In this video, we'll talk about how we can view the integral as a net change over some interval and see how that can be applied to physical problems. We're looking at another application of integrals here, and that is to compute the net change from a rate of change. So the second part of the Fundamental Theorem of Calculus is represented as the following. If I integrate from a to b f prime of x dx, I get f of b minus f of a. We've talked about before how derivatives represent the rate of change of some quantity. That is how fast it's changing at a certain point in time. And the expression here says if I integrate my rate of change between two endpoints, I get the net change or total change of that function over the same interval. This means if I want to find the total change of something, I can just integrate its derivative, and that will give me how much it's changed over this time frame. Another way to think about this is the fact that differentiation is the opposite of integration. Gives us that if I want to go from a thing, how fast it's changing, I use a derivative. If I want to go back from how fast something's changing back to the thing itself, or how much the thing has changed overall, this is where we need the integral. And this concept here is what we're talking about here, using this integral to model the net change of some quantity. So some examples of how this might look like. Assume that water starts flowing into an empty tank. The flow rate is given by r of t, which is our rate, is 4 plus 2 root t liters per minute. After 4 minutes, how much water is in the tank? Well, how much water is in the tank would be the volume at 4 minutes. And because the tank starts empty, this is the same thing as the volume at 4 minus the volume at 0. By the fundamental theorem, this should be equal to the integral from 0 to 4 of the rate of change of volume, dt. Now, what is that rate of change of volume? Well, it's how fast water is being pumped in the tank. This is my r of t. So to find this volume, v of 4, which is equal to v of 4 minus v of 0 because the tank starts empty, is the integral from 0 to 4 of r of t, which is 4 plus 2 root t dt. To now find this, I can just anti-differentiate this function. So I'm going to get 4t plus 2 times t to the 3 halves over 3 halves, plugging in 0 and 4. This is a commutative notation you'll see for this sort of process. I'm anti-differentiating to get to this function here, and I'm plugging in the values here and here. So in general, we use notation f of x plugging in a and b to mean f of b minus f of a. It's a shorthand, but it makes this look a lot nicer when you're trying to actually work out these problems. So this gives me here 4t plus 4/3 t to the 3 halves from 0 to 4. If I plug in 0, I just get 0, so I can just plug in 4. 16 minus 4/3 times 8, and then minus 0. 16 minus 32/3 is then 16/3. Since the problem talked about liters per minute, this is in liters. So basically, if you can set up a problem in which case you need to go from a rate of change to the thing itself, you integrate. You find the antiderivative and you plug in the endpoints, and that'll give you how much the thing has changed over that same interval. Another example, find the displacement over the time interval from 1 to 6 of a helicopter whose vertical velocity at time t is given by v of t is 0.02 t squared plus t feet per second. Again, you want to go from velocity to displacement. This means integrate, because differentiation would go the other way from the position back to the velocity. The displacement should be the integral from 1 to 6, 0.02 t squared plus t dt. I can do the antiderivative, 0.02 over 3 t cubed plus t squared over 2 from 1 to 6. And I can plug in those numbers to get my final answer. And that would give me the displacement in feet. That's the idea of using the integral as a net change and how you can solve problems and word problems that say, find how much this has changed over some time interval and use the integral to solve those problems. Especially easier now that we have the fundamental theorems of calculus, we can just use antiderivatives to get there and have to worry about Riemann sums to get us to these final answers.